Have you ever stopped to think, if these really cutting-edge AI models, the ones writing poetry, acing exams, do they actually get the world like we do? Like, down to the really basic stuff a toddler understands. Today, we're going to dive deep into a pretty groundbreaking research paper. It's called Core Knowledge Deficits in Multi-modal Language Models.
Yeah, it's a fascinating piece.
And our mission really is to unpack its findings. They're kind of surprising, and they challenge, how close we think these MLLMs are to real human intelligence. We're basically going to follow the paper structure step by step.
It's super important right now because the hype around these models, multimodal large language models, MLLMs, it's huge. I mean, they're trained on just vast amounts of web data.
Billions of parameters.
Hundreds of billions, yeah. And they're genuinely surpassing expert humans in certain, knowledge-heavy, reasoning-intensive tasks.
We're talking things like Google's Gemini, OpenAI's GPT-4o.
Yeah.
The paper points out it goes way beyond just language, too.
Exactly. What's really fascinating is how these skills reach into complex perception and reasoning. We've seen them get really good at chart understanding, geometry, math, even action recognition and prediction, often matching or, even beating human performance in those complex areas.
Okay, let's unpack that.
Yeah.
Because, despite those amazing high-level skills, the paper hits you with this kind of perplexing reality. These top-tier MLLMs, they still do worse than humans on really simple, almost basic tasks.
Yeah, it's a real paradox.
It is.
And it begs the question, right? Why do they struggle with stuff that's just intuitive, effortless for us humans? Like just counting a few things or seeing something from someone else's viewpoint, spatial stuff, how time works.
Common sense, almost.
Basically. It really nails Moravec's paradox. The hard stuff of computers is easy for us and vice versa. What we find easy, like perception and mobility, they find hard.
And the researchers, they have this core idea, this hypothesis.
Yeah.
They think these gaps in the MLLMs come from missing something they call core knowledge. These fundamental cognitive abilities that, humans seem to have baked in from early childhood. And these basics, they argue, underpin all the advanced stuff.
Right. And to actually test this idea properly, the paper introduces something new, a benchmark called CoreCognition.
CoreCognition.
Yeah, and it's the first really big benchmark specifically designed for this core knowledge idea. It draws really heavily on developmental cognitive science, how human babies and kids actually learn and figure out the world.
So it's not just throwing random hard questions at the AI. It's structured around how our intelligence develops. That sounds like a pretty high bar.
It is. It proposes this taxonomy, this structured set of 12 core abilities. They cover the whole spectrum from really basic cognitive skills all the way up to more advanced reasoning. And the data set itself is substantial, over 1,500 samples with more than 95 examples for each concept. So it's pretty robust.
All right, let's dig into those 12 abilities then. What are they? You said they're based on cognitive development.
Yeah, they map roughly onto stages like Piaget's. And they're things we totally take for granted, but they're foundational for how we even perceive reality. Let's maybe walk through a few.
Yeah, let's start with boundary. Sounds simple, but crucial maybe.
Totally crucial. Boundary is basically the understanding of where one object stops and another starts. Simple, right. But without it, you can't even have the concept of an object. It's just stuff.
Okay, separating this from that. Got it.
Exactly. Then there's continuity. That's our sense that objects stick together. They're unified things that persist across space and time. Think about a train going into a tunnel.
Right.
It's still one train inside, even if you only see the front going in and the back coming out later. That's continuity.
And the classic one, permanence. Peekaboo.
Peekaboo is the perfect example. It's knowing objects don't just blink out of existence when we stop seeing them. Your face is still there behind your hands. For an AI, that means tracking an object even when it gets hidden or occluded in a scene.
Okay. What about spatiality? Sounds a bit more abstract.
It's our sort of built-in grasp of how space works, Euclidean properties, how things relate spatially. There's that classic developmental test, the A not B task.
Oh, yeah, I've heard that.
Where a baby sees you hide a toy under cup A multiple times, then sees you hide it under cup B, but they still look under cup A. It shows their spatial map is still developing. We adults do incredibly complex spatial reasoning constantly without thinking.
Okay. Then perceptual constancy. What's that?
That's understanding that an object's properties, like its size or color, stay the same even when our view of it changes. Like you throw a red ball far away, It looks smaller, maybe the light hits it differently, but you know it hasn't actually shrunk or changed color.
Right, the object itself is constant.
Exactly. And AI needs to separate the perception from the reality of the object.
In conservation, pouring water between glasses. I remember that from psych class.
A classic. Yeah, conservation is understanding that certain properties, like volume or number, stay the same even if the object changes shape or arrangement. Pour water from a tall, skinny glass to a short, wide one, a kid eventually gets that the amount of water hasn't changed. AIs often get tripped up by just the visual change.
Perspective taking, that feels very human.
It really does, and it's super complex. It's not just seeing what someone else sees physically, but also understanding their mental state, their intentions, crucial for, social stuff.
Definitely. Okay, then hierarchy.
Hierarchy is about organizing things, putting objects or concepts into categories and subcategories, like knowing that all dogs are mammals, but not all mammals are dogs. That's class inclusion. Or transitivity. If A is bigger than B and B is bigger than C, then A must be bigger than C. It's about logical structure.
Makes sense. How about intuitive physics?
That's our gut feeling for how physical stuff works, how things fall, inertia, basic mechanics. We just sort of know how objects will behave. And linked to that is intentionality, understanding, reading the why behind someone's actions.
Like seeing someone reach for a cup.
And knowing they probably want to drink, yeah. Not just seeing an arm moving, understanding the goal.
Okay, in the last two, mechanical reasoning and tool use.
Right. Mechanical reasoning is more about understanding systems, how parts interact, cause and effect, inferring actions needed to get to a certain state. And tool use is, using objects as tools to achieve a goal, seeing a doorknob and knowing it affords pulling or turning.
Wow.
These are all fundamental building blocks, and that's what CoreCognition is designed to probe in these MLLMs.
Yeah, quite the list of ability. So how on earth do you actually test an AI on these? It sounds incredibly tricky. The paper must have gone into a lot of detail on the methodology, right? Let's talk about how they built and tested CoreCognition, the dataset curation firm.
Oh, absolutely meticulous. They set really strict criteria for the test examples. First was discriminativeness, meaning the questions had to be designed so that a model without that specific core knowledge would definitely get it wrong. You couldn't just guess or rely on some surface pattern. It forces the model to actually use the knowledge or fail.
Okay, so no lucky guesses.
Exactly. Second, minimal confounding. They tried hard to make sure each question tested only the target ability without accidentally relying too much on, say, basic object recognition or overlapping with another core concept they were testing elsewhere. Keep it clean.
Makes sense. Isolate the variable.
Right. And third, minimal text shortcut. This is key for multimodal models. The answer couldn't just be figured out from the text prompt alone. The model had to genuinely process and understand the image or video content.
Okay. That makes a lot of sense. Who actually designed these tests? It sounds like you need people who really understand cognitive development and AI.
They did. They had 12 annotators, all with college-level backgrounds in fields like cog-sci, computer science, or stats. So yeah, interdisciplinary expertise. And they got creative. Like, for object permanence, they literally adapted those classic baby experiments, hide a ball under one of several cups, shuffle them around. And the model has to say where the ball is now. It directly mirrors the developmental research.
That's brilliant. Translating baby science to AI testing. Where did all the images and videos come from?
All over. The internet, existing public data sets, they used AI to generate some synthetic stuff, used simulations, and even did some original recordings themselves, a real mix. And then crucially, every single question-answer pair went through 2 rounds of independent cross-validation.
By different people each time?
Yep, separate groups of annotators checking each other's work. And even then, they did another round using Amazon Mechanical Turk, getting responses from 20 regular human annotators.
Why the MTurk step?
To check if the questions were clear and unambiguous to non-experts. If lots of humans got a question wrong, they'd flag it and re-examine it, really ensuring the benchmark itself was solid.
Okay, that's some serious quality control.
Yeah.
Now, the logistics. Testing, 230 MLLMs? From 1 billion to over 100 billion parameters? That sounds like a massive headache. Computation time, different software setups.
It's a huge engineering challenge. They had to build a whole scalable system just to run everything. But beyond just running them, a really big problem was handling the outputs. MLMs don't just give you A, B, C, or D. They often give free-form text answers.
Right. They explain their reasoning or just phrase it weirdly. How do you score that consistently?
That's the tricky part. If you evaluate it badly, you might think a model failed when it actually got it right, or vice versa. So they came up with this clever system they called hybrid matching.
Hybrid matching.
Yeah. First, it tries some smart rule-based pattern matching to see if the answer fits a template if that doesn't work cleanly.
That probably happens a lot.
Definitely. So if the rules fail, it falls back to using an ensemble of 4 other powerful LLMs models like Qwen 2.5, Llama 3.1, basically asking them to interpret the answer.
Using AI to judge AI.
Kind of, yeah. But here's the catch. They only accept the LLM interpretation if at least 3 out of the 4 agree on what the answer was. It's a really high bar for consensus to make sure it's accurate. It worked remarkably well, actually.
Impressive. What if a model just kept giving garbage outputs, stuff that even the hybrid matching couldn't figure out?
Yeah, that happened too. Some models just consistently fail to produce valid, interpretable answers, so they set a threshold. If a model had a fail rate of 20% or more on just generating a parsable output, they excluded it from the final analysis.
Okay, filter out the ones that can't even play the game properly.
Exactly. That left them with 219 models whose results they could actually trust. That whole rigorous process, the careful benchmark design, and the evaluation strategy, that's what makes the findings so powerful.
All right, so they built this incredibly rigorous benchmark. They figured out how to test hundreds of models fairly. Now, for the moment of truth, what did the experiments actually show about core knowledge in MLLMs? And you hinted the findings are, well, pretty interesting. The first big one, a clear core knowledge deficit.
Yeah, it's quite striking when you see the data. The models generally do much better on those higher-level cognitive tasks, things associated with, say, Piaget's formal operational stage in humans.
The complex reasoning stuff.
Exactly, stuff where they often match or even beat humans. But they really, really struggle with the lower-level abilities, the foundational stuff, things humans master in the sensoromotor and concrete operational stages, basically, infancy and childhood. The gap there is significant.
And humans don't show that gap, right? We're good at the basics and the complex stuff builds on it.
Precisely. Humans are consistently high-performing across all these stages in the benchmark. We don't suddenly forget object permanence when we learn algebra, but the MLLMs show this big drop-off at the foundational level.
Are the numbers bad?
They are significant. Even the very best models, we're talking top proprietary ones like GPT-4o, they lag behind average human performance by quite a margin on these lower-level stages. Like GPT-4o was over 21% worse on average.
Wow.
And interestingly, it wasn't a clear case of proprietary models always being better than open source ones on this stuff. It seems like a more fundamental issue across the board.
So it's not just about having the biggest model or the most money. It's something deeper.
That's what it looks like. For instance, perspective taking. Models were markedly worse than humans. The paper suggests this might be because they lack a real capacity for mental simulation.
Yeah.
Actually imagining a scene from a different viewpoint.
Okay, so they're shaky on the basics. Does that weakness actually matter for their high-level skills? Or can they just sort of bypass it? This leads to the next finding, right, about developmental scaffolding.
Yeah, this is maybe even more revealing about how MLLMs differ from us. They found that these core abilities show really weak correlations across developmental stages in the models. There's an absence of that scaffolding, meaning in humans, living the basics absolutely helps you learn the more complex stuff later. You build on foundations. Crawl, then walk, then run. But in MLLMs, performance on high-level tasks isn't reliably connected to how well they do on the low-level stuff that should underpin it.
So they can be good at advanced geometry, but bad at knowing if a hidden object still exists.
Yeah.
The foundation isn't really foundational for them.
It doesn't seem to be integrated in the same necessary sequential way it is for human development. It's like the skills are learned more independently or maybe through shortcuts that bypass the need for true foundational understanding.
But hang on. In humans, doesn't core knowledge predict general intelligence? The paper does say that performance on core knowledge is predictive of higher level abilities, even in AI, right?
Yes, it does find that. So it's a bit nuanced. While the scaffolding seems weak or broken, doing well on the CoreCognition benchmark does generally predict better performance on other high-level AI benchmarks, like Seedbench 2.
So core knowledge is important for overall capability, even if it's not built up the same way.
It seems to be correlated, yeah. If a model does happen to have better core knowledge, it tends to perform better overall. There are exceptions, though, like performance on tasks that are mostly about text, like understanding charts purely from text descriptions, chart QA, didn't correlate much with this visual physical core knowledge.
Okay, so core knowledge matters, but it's not being learned progressively. What about scaling? The usual answer in AI is just make it bigger, more data, more parameters. Does that fix the core knowledge problem?
This is maybe the biggest surprise in the paper. The answer seems to be No, or at least not effectively. They found that MLLMs show limited or even no scalability on these low-level abilities compared to how they scale on high-level ones.
Wait, really? Bigger models don't get better at the basics?
Significantly less so. For most of those foundational abilities, 7 out of the 9 in the sensory, motor, and concrete stages performance improved much less with increasing model size than it did for the higher-level ability.
That's wild.
And get this. For perspective taking, performance actually got worse as models got bigger.
Worse.
They suspect it's due to an increasingly strong egocentric biases. As the models get larger, they might rely even more heavily on patterns learned from the massive text data, which often describes things from a single default viewpoint, making it harder to mentally simulate other perspectives.
So just scaling up isn't the magic bullet for core knowledge. You can't just brute force fundamental understanding.
That's the stark conclusion here. It really challenges that core assumption that bigger is always better for all aspects of intelligence.
Okay, if scaling doesn't work, what about making them reason more? Explicitly training them for reasoning or using techniques at test time that let them think longer. Does that help bridge the core knowledge gap?
They looked into that too. And again, the answer was largely no. Giving models reasoning capabilities or using test time scaling methods didn't really give them a clear advantage on these core tasks compared to models that were just fine-tuned on instructions.
So more thinking time doesn't fix the underlying lack of intuition.
Not significantly. Across 10 of the 12 core abilities, there were basically no meaningful differences. For perceptual constancy, maybe a tiny improvement with reasoning models, but for perspective taking, they actually did worse again.
Huh. Worse again.
Yeah. Overall, maybe a tiny, non-significant average bump. The paper suggests this points to current architectures just struggling with grounded reasoning. The knowledge isn't connected to the world in a way that lets reasoning effectively use it.
And they link this back to older AI ideas.
Right, insights from connectionism. The idea that when knowledge is sort of smeared across millions or billions of parameters in these distributed representations, it's actually really hard for the model to reliably pull out and use specific pieces of structured knowledge, like core physical principles, when it needs them for reasoning. It's not neatly organized.
That's a deep point. It suggests maybe a fundamental mismatch between the architecture and the kind of knowledge we're talking about. Okay, this leads us to the final, really crucial experiment in the paper, concept hacking. This feels like the ultimate test. Are they really understanding, or are they just clever fakers?
Exactly. Are they genuinely grasping the concepts, or are they just exploiting statistical patterns, shortcuts, spurious correlations in the data? This concept hacking experiment was designed to tease that apart.
How do they do it?
It's a controlled experiment where they manipulate the key causal features within the images. They compare how the model does on a standard version of a task versus a manipulated version where the underlying causal structure is changed, sometimes even inverting the expected outcome.
Okay, and based on how the model performs on both versions, you can categorize its understanding.
Right. The paper lays out 4 possibilities. You could have true core knowledge. The model gets both the standard task and the manipulated task.